Mm. Hello, everyone. We are a group of 5 graduate students from San Jose State University doing masters in data analytics. And this particular project, Adaptive Machine Learning for DDoS Detection, is being done under the guidance of Professor Shiyu Chang for our course, Machine Learning Data 245. Um, Coming to our project, today internet of things is like there are about 25 billion of devices that are connected worldwide, and this technology has revolutionized the traditional way we do our things. But however, these connections raise security and privacy concerns, and one of them is DDoS attacks. What are DDoS attacks? DDoS are distributed denial of service attacks, which attempt to interfere with the regular network traffic by flooding the target website with so much of traffic that the website might become down, and the legitimate users cannot use the website. This can severely impair network functionality by taking use of uh, availability of numerous compromised computer systems to impact the target servers as well as the associated infrastructure. So, to tackle these attacks, we need robust security measures. Traditionally, DDoS detection are rule based and static. It detects attacks based on traffic volume of the attack and sends an alert. However, there are limitations to this rule based detection. These rule based detection cannot identify low scale attacks. Therefore, to mitigate this, we aim to develop machine learning models that not only detects these attacks but also learns from the evolving behaviors for enhanced and proactive detection from ongoing data and adjusting to new threats in real time. And these machine learning algorithms improves detection rates and reduces false positives. So, and this is very essential to protect our IoT environments. Coming to our project, so this we have done using Google Colab on cloud, and these are all the libraries that if imported. We've used Pandas, NumPy, Matlob, and Matplotlib, and Seaborn for visualization, and we've used scikit-learn library for our models. So coming to the data set, we've used a NetBIOS data set. So this data set basically contains 3.4 million rows of data and about 88 columns in total, which includes the target label, which tells us whether the network traffic is benign or whether it is NetBIOS, which is attack. So we first proceeded with data cleaning and data pre-processing steps to make our data, to enrich our data for our modeling. So, yeah, so we first cleaned all the columns uh, with their white spaces. If there are any white spaces, we have stripped those white spaces, and then we've checked for null values. There were totally 6 null values, 6 rows of null values in our data set, and we've removed all those 6 rows, but only on the rows where only the target label is NetBIOS, because as we sweep, the benign class is only 1300 rows, so we do not want to lose any benign row. So we've removed null values that contain the target label as NetBIOS. And after cleaning them, after removing all the missing rows, we've checked if there are any duplicate rows in our dataset, which is 0. And after this, we observed that there are some infinite values in our columns. So this might be due to data entry error. So we've removed all the rows that contains these infinite values because they do not add any value to our machine learning models, and it might be a problem during modeling. So we've observed that there are totally about 130,000 rows. And since our total number of rows in our data set is about 3.4 million, and this 130K is very insignificant amount, so we've removed those entire rows. And here there's an overall, these are the 88 columns that we have. And we've seen that the forward header length and the forward header length point one, these two are redundant rows. They're repeated twice. So we've removed the one of the row. And then we've done a basic exploratory data analysis for our label column. We have already mentioned, the net BIOS is about 3.4 million and the benign class is about only 1300 rows. So that's why even in the bar plot, it is not able to, detect the benign class tables. And after the initial data pre-processing, we've went with the data preparation for data modeling. And here we've deleted all the columns that do not add any significant value to our target label. These some of these rows includes unnamed, the destination IP address, the source IP address, which do not provide any information about the target label. So we've removed all these columns to reduce our dimensions. And finally, after removing all these columns, we've got about 71 features in our data set. And now we've checked for any outliers in the data set. So we've observed that there are so many outliers, and we've plotted for one column, which is flow duration. Here we observe that there are so many outliers for the class net BIOS, and there are none for the benign class. And we've removed all these outliers for to enrich our data set for effective modeling. So after removing outliers, we've got about 2 million rows. And later, we've done label encoding for our target variable. Since our target variable in the column is in the form of net BIOS and benign, we've assigned ones, and we have done categorical encoding to this target variable in the form of 1 and 0 for the machine learning models to understand them. And later, we've split the data into target label and features. X is the data frame that contains our features, and Y is the data frame that contains our label. So, like we've already mentioned, that the um, net BIOS rows are about 2 million when compared to the benign rows. So uh, this is this is significant data imbalance. So we try to balance the data set for effective modeling. So to address this problem, we've employed an integrated data sampling strategy, which is a combination of undersampling and for the majority class and oversampling for the minority class. For undersampling, we've used random undersampler with a sampling strategy of 0.2, meaning that after undersampling, the majority class instances will be in the ratio of 5:1 when compared to the minority class instances. So this, from the 2 million rows that we had here for the majority class, that has been undersampled to only about 6,495 rows, which is 5 times the minority class samples. And after undersampling, we've split the data into train and test sets in the ratio of 80:20. This is done before oversampling because we want to maintain the integrity of our test samples, because in oversampling, algorithm the smart algorithm that we use, it generates synthetic samples, and we do not want to test our models on synthetically generated samples. So that's why we split our data set into train and test before doing oversampling. So here we've plot a bar plot of all of our uh, instances after undersampling. So after the train and test, we've done the oversampling using SMART. So here we've used a sampling strategy of 0.5, which means that it generates the minority class samples in the ratio of 2:1 to the majority class. So after doing small, that is the oversampling, we've got about 5,208 samples in our majority class, and the previous 1,209, the 1027 class, has been increased to 2,604. So this is oversampling. And after oversampling, now we've got a balanced data set. And since we have dimensions of 71 in our data set, we've reduced these dimensions using PCA. And we've retained 95% variance in our data set. So for after retaining 95% variance, we've got about only 19 features in our data set, and this we've used it for training. Here we've defined an evaluate underscore predictions function to evaluate all our metrics that we need for modeling, like accuracy, precision, recall, F1 score, and classification report. Next, this data set is used for modeling. Next will be held by Niharika.
Okay.
Yeah.
So after getting clean and transformed data sets, first we built a linear regression model as a baseline model for our project. In that, we got 100% of accuracy for all evaluation methods that suggest our baseline linear regression model might be overfitting. And then we applied the L1 regularization with a random state of 22 and maximum iteration of 1000. In that also we got 83% of the accuracy. So next is our random forest model that has been implemented with the depth of the 10 and the 42 random states. Similarly, for random forest also we got 100% of accuracy, and after before performing any hyperparameter tuning, after performing hyperparameter tuning also we got 100% of accuracy in that model for all precision, recall, F1 and accuracy. Following the random forest for KNN, also we got 100% of accuracy, and in that also we use 42 random states. Next is XGBoost. We achieve 83% of accuracy for XGBoost as well. And again, for SVM, we got 100% of accuracy. So our next is our decision tree. Before regularization of decision tree, we gain full accuracy like above all the models. And after regularization, as also we got 100% of accuracy. So now, for better understanding for comparison of all models accuracy, we plotted a graph which describes our models might be overfitting. Expect XGBoost and linear regression, we got 100% of accuracy for all models. In last, we saved our balanced sample data set for the future studies.
Yeah.
So to conclude this, I would say our goal was to create an adaptive machine learning model which is capable of detecting DDoS attacks within IoT networks, overcoming to the drawback of traditional detection methods. We accomplished this by utilizing the extensive need-based dataset, which encompasses details network traffic and server logs. Through the pre-processing steps such as normalization, feature extraction, and data balancing using techniques like Smoothie, we prepared our data set for model training, and then we have implemented all the above described models, and we got almost a full accuracy in the all models. This adaptive methodology, which required minimal human interactions and provides a robust and flexible solution for DDoS detection, and which improving network security and reliability for both business and individual, and helping to prevent financial losses and servicing disruptions. And in last, I would like to extend our deepest appreciation to our professor Siu Cheng, our esteemed instruction for the machine learning course at San Jose State University, for his invaluable guidance and support throughout our project. We are also grateful to the University of Canada, which providing extensive net bias dataset, which we used for our entire project in that, and that played a pivotal role in our research. Thank you.
Yeah.